All right. Cool. We're recording now. Okay. So I'll share my screen. I've put the file up in our general channel. If you want to grab it and follow along. If you prefer just to kind of like sit back, watch and ask questions, that's cool also. So it's up there if you want. Oh yeah, share screen. Okay, make this a bit bigger. All right. So first up, I always like to load tidyverse because I know I'm going to be using it. Okay, and then I need to grab the CSV file. I'll call it df, and I'll do read underscore CSV. You note that I'm in my data courses on. All right, and where did I put that? I think it was in data, and I stuck it, oh yeah, designed experiment, spelled correctly, .csv.
Do you have the file up in your repository?
No, the file, I just stuck it on Teams.
Okay.
So if you go to Teams, it's in general, right there, fake experiment data.
Okay, cool.
All right, since I'm a good person, I'm gonna go ahead and write comments. So let's run those. All right, we've got DF in there, 180 observations of 5 variables. Let's take a look at those. So we've got replicate, agricultural treatment, which is a logical true-false. We've got water saturation, plant species, which is a character, and then plant mass. So I just made fake data for plant mass. What is our dependent variable that we're interested in here?
The agricultural treatment.
What makes it dependent?
Shoot, that would be a plant mass because it's dependent on everything else.
Yeah. Plant mass is actually our dependent variable. It's the variable that depends on the other variables. Agricultural treatment, we decided whether we put this treatment on the plants or not. There's no, I can't conceive of a way where plant mass would change the agricultural treatment. And so it's actually an independent variable. So the one we are measuring as our output is plant mass. So that's our independent variable of interest. So let's look at this. It looks nice and tidy. Okay, we can do some summary stats. Okay, so we can summary df plant mass. All right, that gives us our first quartile, minimum, median, mean, third quartile, max. Interesting. I could change that to plot just to kind of get an overview. And okay, so there's our plant mass over index. What does index mean in this case?
The number of the observation.
Yeah, it's actually just the order, the rows. And so if you can see that it's going up, then it starts over. It goes up. So in our data frame, that kind of makes sense. We got water saturation, 10, 20, 30, 40, 50. It's going up. And then it starts over, 10, 20, 30. Okay. So, okay, that makes sense to me. So we're just kind of get a feel for data. First plots. All right, ggplot, df, aesthetic, x equals plant mass, I'm doing x for a reason, plus geome density, because geome density only wants an x or a y. Okay. What does this show us about our plant mass overall for the entire experiment? How does it relate to this summary here? There's our minimum, 1.69. That looks about right. 1.69 should fall about right there. Our max is 8.08. Yep, there's our max. The median, 4.5-ish. So right about here. So there's our median. Our mean is right about the same. Okay. So this is just showing us what we call our distribution. Okay. Now, a lot of statistical tests require that the data be distributed normally. You may have heard that, right? This looks pretty decent. It's approximately normal. Definitely good enough for the test. It's not going to break any of our stats tests. But let's add a couple things here. X equals plant mass, color equals plant species. And I'm actually going to change color to fill since we're making these density shapes. Geome density, and I'm going to change alpha 0.5 so we can see through them a little bit. Okay. What's going on here? Any thoughts?
Different plants have different distributions of plant mass.
Yeah. Okay. So just by visualizing it, we get that. And I'm not certain at this point, but I'm guessing that plant A and B basically are not too different from each other. And plant C looks a bit different. It seems to be bigger overall. So how does this respond to agricultural treatment? So I'm going to do a facet wrap as a function of agricultural treatment. Okay. That seemed to change things a little bit. What's another variable we haven't taken into account, though?
Water saturation.
Yeah, that was something we set deliberately. 10 different levels of water saturation. How would we show this?
Could you facet wrap it as a function of water treatment, water saturation?
Sure. It's going to be a lot more facets. So this is definitely an interesting pattern. It looks like plant B is responding very differently from A and C at low water saturations. And basically responds to water saturation at a different rate than these others. Okay. So I'm going to make another type of ggplot here. ggplot df x no, aesthetic. X equals, and down here I'm going to put water saturation and our x-axis. Our y, I'm going to go ahead and stick our independent variable, plant mass. Let's do color equals plant species, and then do a geom point. Let's take a look at that. Okay. Coming around to something here. Maybe. Let's add a geom smooth and force it to be a linear straight line. So method equals LM for linear model.
I have a question.
Yes.
How would you? Oh, never mind. It automatically did it. Okay. I was gonna say, how would you do a smooth line for each species, but it just did it.
Now the reason it just did it is because I had color as an aesthetic in the main call, and so geom smooth, since it's making a line, those have a color aesthetic associated with them, and so it'll do a different one for each plant species. That makes sense. So what do you think? How does water saturation affect plant mass for these three species?
For all of them, it increases the plant mass, but plant species C seems to have the most positive correlation with it.
It's got the stronger result. In statistics, what we're looking at is actually like the slope of that line, right? The equation for a straight line is y equals mx plus b. If you remember that, m being the slope, all right? So that is going to have a higher, a bigger slope than the others, okay? And they're all positive slope. Now, as somebody who's analyzed data a bit in the past, I see these little green dots here that seem to fall way out of the line. Any ideas what might be going on there?
To me, it looks like plant mass for species B is not strictly tied to water saturation at the lower levels.
Right. That's my gut also when I see this. Anyone else? I have an explanation as to what we're missing here.
You could do a G test to toss out any outliers, right?
You know, we don't actually like to do that. It's considered kind of bad form in data analysis because those outliers are real observations, right?
Could
We
it
don't
be
want-
the treatment?
Ah, what do you mean?
So those outliers could be the positive treatment, and that's what's affecting the plant mass.
We have not taken treatment into account, have we? Our agricultural treatment. What you're looking at on the screen right there, those lines, that's a statistical model. So congratulations, you already know how to render one in ggplot. Behind the scenes in ggplot, when you say geom smooth method equals LM, back in the background, it's actually running a linear regression on your data. In this case, it's a multiple regression, okay, which I don't even think they get to in Stat 2040. All right, that's like the very end of the class. So we're starting at the end of stats with multiple regression. It's that easy. It's ggplot's doing that automatically.
I have a question for you.
Yeah.
So in one of the like week 9 reading things that you had us do, it talks about how the explanatory variable or the independent variable should usually be on the x-axis, but I think in this case you put it on the y. In this case, is that a better option to put it on the y, or should we
I think you might. I know what you're talking about. I remember reading that in there. The independent variable is not the explanatory variable.
Oh,
It's
Okay.
the variable that's being explained. So if that helps. The
Yeah.
rule of thumb, yeah, kind of standard practice is to put the variable of interest, your independent variable, on the y-axis.
okay.
You don't always have to. It's not a real rule, but it's what people expect in a graph. Now,
Okay.
here we're saying as water saturation goes up, it causes plant mass to go up at this rate for each of these species. Okay. But what we are picturing right here is not taking into account agricultural treatment at all. So we're going to have to change this a little bit. So let's think. I can do color equals agricultural treatment, GM point plus LM, and then add a facet wrap based on plant species. Ayo. That's a different way of looking at things. Now we're taking into account water saturation, plant species, and agricultural treatment all at once in the same plot. What do you see here that's different? The points are all going to be basically in the same spot, but our little trend lines have changed a bit.
Is it just me, or is it only? It's not showing species, really, is it?
It actually is A, B, C.
Oh.
Yeah,
Sorry.
sorry. Each species is its own panel. So if you remember back here, species B is the one with those weird looking outliers, right? And we're saying like, hey, this trend line doesn't do a great job for B. When we add in agricultural treatment, it's still not doing a great job, but it's better than it was before. It's changed the slope. You see that? So now we're allowing two different slopes for plant B, two different slopes for plant A, excuse me, and two different slopes for plant C. So give me a shot. Try to summarize what we're seeing in this plot in plain English.
So for A and C, they have pretty strong correlation with how much water they get versus their growth, with agricultural treatment just barely increasing plant mass, while species B, getting agricultural treatment really increases the initial plant mass. But it also lessens how much it looks like water saturation actually helps it out, because the slope isn't as steep as when there isn't any agricultural treatment.
That was beautiful. I loved it. That's what we're seeing. It's almost like we could say the importance of agricultural treatment diminishes in plant B with increasing water saturation. The slope is less steep than if you don't have the agricultural treatment. So whereas agricultural treatment does increase plant mass in every one of these species, its effect depends on water saturation. So I hope this kind of is clear. The effect of agricultural treatment for plant B is greater at low water saturation. There's a bigger separation between these two trend lines than at high water saturation, where they're almost like overlapping. Okay. So I'm seeing this and I'm thinking this is already this plot right here is essentially our story. I think it's working. It's kind of telling the whole picture of how water saturation and agricultural treatment and plant species all interact with each other to affect plant mass. So what's next? I mean, think about this as a research experiment that you actually designed and carried out. You filled out your Excel spreadsheet, imported it into R, made this pretty plot, and you can describe the plot. You found a story in there. What's left in our data analysis lifecycle?
Let's see. So modeling to see if it's a consistent story.
Is it real? Yeah. We want to know if we're being dumb and seeing patterns where there aren't any in our plot, or if we can back up with statistical likelihood whether these patterns are likely to be actually in there. Now, in the background, ggplot's actually kind of doing that for us, right? It's actually calculated this multiple regression model in the background for us, but we want the slope of those lines, don't we? That's what you're going to be asked on a stats test. So let's take a look at how that works. First, I'm going to go back up here and add another library or another package. Modeler. Modeler works with the tidyverse, and it's for modeling. Okay. And we'll use it in just a second. So try some linear models. Models. Is that how you spell models? No. There we go. Okay. So in R, there's a bunch of model families already built in. We've got analysis of variance. We've got simple linear models. We've got generalized linear models. Whoop. Okay. I'm going to start out with a GLM. Okay, this is a generalized linear model. It's usually a pretty decent spot to start. If you look through like assignment 8 and some of the resources, there's kind of a rubric for how to pick what family of models we're talking about. This one's usually kind of a safe pick if you've got a continuous response variable, okay, and continuous plus categorical predictors. So it all kind of depends on the type of variables you're looking at. But here we've got a categorical variable predicting agricultural treatment, categorical one predicting here, plant ABC, and a continuous predictor down here, water saturation. And then our plant mass is continuous. So start with the GLM. It's kind of nice and basic. Okay. The first thing to do is tell it where to find the data. Data equals df. Okay. And then it wants a formula. So formulas in R are written with a left side and a right side separated by the little tilde, which means as a function of, if you remember. So I'm looking at plant mass as a function of what?
Water saturation.
And just that? Okay. So we'll look at plant mass as a function of water saturation, and behind the background R will be picking the best fit line where water saturation is explaining plant mass. So I'm going to save this as mod 1. tidy this up so it's easier to read. Okay. So there's our data, there's our formula, and I'm gonna hit Control Enter and run it. It's done. So now we got mod 1 up here. It's a list of 30 things. I can say summary mod 1. Let's take a look at our output here. All right, there's a lot going on. First is the call. That's just the formula and the model family. So it's saying here's what we ran. A generalized linear model where plant mass is a function of water saturation, and here's the data we use to fit that model. Okay. Deviance residuals. Anyone know what those are? Residuals? I guess that's a no. It's how close to our trend line is the actual data. So it's like the distance of this dot to the line, the distance of that dot to the line, right? If it's exactly on the line, the residual is 0. So it's essentially like the residual is what's left over that our model couldn't explain. All right. Is that making any sense? Please let me know. It's weird just talking to myself.
Yeah, that makes sense.
Kind of. Is that
Kind of. Okay.
is that taking like an average from all the dots that aren't along your line, or
It's actually got a residual for every point, and I can access that. I can say mod1 $, since it's a list, and do residuals, and here's what it's showing me. So for the first observation, it was negative 0.657 off, right? So it was a little bit off of that line.
okay, that makes
Second
more
one
sense.
yeah, so it's a residual for each of them, and then what's actually reported in your summary is just the min, first quartile, median, third quartile, and max. So it's kind of summarizing all of those 180 residuals. If I wanted to plot them, I could just wrap mod1 residuals in a quick little plot like that. And so here's how far off of our true model being 0 here. Okay. So in other words, our residuals, and this is just kind of a summary of some basic stats about them, is what's left over in our real data, which is messy, how far it is from the statistical model we tried to fit to it. Okay. So that's our residuals. It's like a summary of how good of a fit our model was. And then here's coefficients. Okay. Let me do a quick plot of just this. ggplot df aesthetic x equals water saturation, y equals plant mass plus geom smooth method equals linear model, and then I'll do a plus geom point on top of that. All right, so that is our model right there. And here's the output of that model. Okay, so our intercept, 2.15. Hey, look, that's our y-intercept. Remember y equals mx plus b? Okay, this is the b in that equation. 2.15. What's that?
that be your x-intercept?
Nope.
Nope. Okay.
Y is plant mass. So plant mass, according to this model, not necessarily in reality, plant mass is equal to mx, here's x, so m times water saturation plus 2.15. That's our m. That's our slope of the line right there for water saturation. So for every increase of 1% water saturation, our model is saying you should expect an increase of 0.04 grams of plant mass. That's the slope of this line right there. All right, so that's how we get the equation for this line. All right. So that's okay. Let's take a look at our model again, especially our residuals, because look how much scatter there is around this line. Yeah, there's a trend there, but there's that weird, remember the kind of outliers up here that appear to be kind of going down. So one way we can do this is to look at the average residual. So like the average of how far each point is from the line. So I can do mod 1 residuals. And since some are positive, some are negative, it's traditional to just square them all and then take the mean. Okay, so this is the mean squared residuals. And this will just give us a single number, 0.69. So that's the mean squared unexplained variance in our data. So the higher that number, the worse our model is at fitting to our actual data points. Let's make a better model. I don't think I like this one very much. It's got a lot of scatter around it. Let's make one more like that. How do I make that model? And call it mod 2.
Let's see. So would you do plant mass as a function of water saturation, agricultural treatment, and species?
Yeah, let's throw it all in. So we can tell our model what to pay attention to. In this first one, we said, hey, the only explainer variable that I want you to think about is water saturation. But remember, we see in our picture here that agricultural treatment has an effect on this, and so does plant species. So let's say is a function of water saturation plus agricultural treatment plus plant species. Okay, let's take a look at that. Summary, mod 2. Okay. Here's our call. Here's our residuals. And here's our coefficients. There's more of them this time. What are they telling us? What is our b in our y equals mx plus b?
1.41.
Yeah. So there's our intercept has changed a bit. If you remember before it was 2.15. So now in this model, it's saying our intercept is 1.41. The effect of water saturation, that's our slope for water saturation, 0.043. Yeah, so it's about the same. Okay. But it's also given us some other stuff. It's saying the effect of the agricultural treatment being true is 0.776. What's that mean in non-jargon?
Does that just increase plant mass by that value, regardless?
Yeah,
average?
so overall, it's saying the effect of adding the agricultural treatment is going to be an extra 0.77 grams of plant matter based on everything else. So we take our intercept, we add that, we do our slope, we look at water saturation, okay? We then say, oh, if it's the true agricultural treatment, yes, then we add this much to the final value, okay? This is the effect of being plant species B. This is the effect of being plant species C. Plant species A was the first one it saw, and so it kind of leaves it out. That's 0. So it bases the rest on this. So if you're B, they expect you to have this much more on average. Plant species C to have this much more on average. So we're getting a feel for this, okay? Over here, you probably encountered this or will in statistics class. The probability that our t-value is greater than the absolute t-value. That's your p-value right there. And here's 3 stars saying how significant it is. This is basically saying it's as close to 0 as we can measure. So what's that mean with respect to water saturation? Is it significant or not?
It's statistically significant.
Statistically significant, according to our test that's going on, which in the background was a t-test. Okay. What about plant species B?
So I feel like B is significant, but according to our current model, it's not. So
It's
we
not.
need to change it to make it so it is significant, right?
No.
Or so we're just
No.
imagining things then.
You're imagining things.
Well, that's
exactly.
stupid.
Yeah, it is. It's really stupid. That's okay. But what it's actually saying, and this might help you interpret it more, is that since everything's being compared to A, it's saying that B is not actually different than A. And if we look at them, they're about on the same wavelength here, right? But it is saying that being C is different than A. Does that make you happier when you look at this graph and see that B is not significant?
No. Why,
No.
why would it make me happier? Because A and C look a lot more similar to visually than B does to either.
Oh, they've got the same slope, right? But
Yeah.
values of C are actually higher overall than A. This is saying that the value of plant mass for B is not significantly different as far as we can tell from A.
So we need to do something to look at what the correlation between agricultural treatment and what plant mass would it be? Or plant mass and water saturation to make B more
Both
significant?
together. So I'm going to make a third model that'll actually get us there. Mod 3. Now what we did in this first one, we said our data is DF. Okay, yep. We said plant mass is a function of water saturation plus agricultural treatment plus plant species. If I change those pluses to times, little star there, mod 3, summary, mod summary, stop that. Summary, mod 3. Okay, now we've got a whole bunch going on. Look at all this. When I changed it to times, it's basically saying that I'm going to let the slope vary based on agricultural treatment, and I'm going to let the slope vary based on plant species. If I do plus, it's just letting the intercept vary. It may not make sense. I'll show you in a plot here in a second. In this plot, you can see that for A, the slope of the line between the two agricultural treatments looks the same. They're both going up at the same rate. Same for plant C. They're both going up at the same rate. But plant B, those look like different slopes to me. And that's probably what's like bothering you. Am I right?
Yes.
Yeah. They have different slopes. So by changing the plus to times, we're saying, all right, plant mass as a function of water saturation and agricultural treatment and plant species and the interaction between water saturation and agricultural treatment and the interaction between agricultural treatment and plant species. So it's letting our slopes vary for our linear models. You can see that here. When you see a little colon, that means the interaction between. So the interaction between water saturation and the true agricultural treatment, okay, it's going to give us that effect. But what about here? Water saturation, agricultural treatment, and plant species B. It's kind of wrapped around. Let me see if I can make it all show up. Summary mod 3. Yeah, there we go. It's saying that there is a significant effect that only shows up when you look at water saturation, agricultural treatment, and plant species B. For plant species C, it's not significant. So that's actually what we're seeing in our model that's displayed here, is that agricultural treatment does have an effect overall on all the plants. The true agricultural treatment has lifted it up a little bit. Okay. But for plants A and C, the effect of agricultural treatment does not depend on the water saturation. It's the same slope all the way through. But for plant B, it looks to me, and it shows in our stats here, that the effect of agricultural treatment is important, but how important it is varies based on how much water saturation there is. So that's the slope. All right. Let me take a look at these three models. I'm going to copy this, paste, paste. I'm going to look at our residuals for all the models. So here's the first one, second one, and third one. Which one is best?
The last one, because it's closest to 0.
Yeah, it's closest to 0. It's the smallest spread off of the best fit line that we calculated. Okay, so between these three models, I'm going to pick mod 3, this last one. So mod 3 has lowest residuals. So that's just kind of an easy way to, like, this happens quite often. You'll fit your models and you'll do a few of them because you don't know what's really important in your data. You have an idea from your picture, right? And so you make a few graphs and you kind of worm around it and you say, okay, let's try a couple different models and then let's see which one is the best fit for our data. So this is a quick and dirty way of like seeing which model gives you the lowest mean squared residual value. Okay, so we'll go with model 3. We can actually use that model to make predictions. And that should make sense to you. Like, we've got an equation for a line. The equation for that line depends on water saturation, agricultural treatment, plant species, and all their interactions. So our model R package gives us add predictions, which is real handy. We give it some data, which is our data frame. We give it a model, mod 3. Let's take a look. It's really that simple. So here's DF. It's got 1, 2, 3, 4, 5 columns. Add predictions gives us 1, 2, 3, 4, 5, 6. So this new column is called pred by default. You can name it something else if you wanted to. What's in there?
Is that the value calculated by the linear model that we
Yeah,
created?
it's the point on our line, right? So it's basically taking this line and saying, okay, your water saturation is 50. Cool. Moving up 50. Which plant are you? B? All right, cool. Agricultural treatment, true or false? True? All right, then. Boom. So for that, I'm going to give you a 4.82 or whatever. So it's the value on that line that meets all of these. So there's our predictions. I'm going to go ahead and save this as df2, just so we can plot with it kind of easily. We'll make a ggplot with df2. Aesthetics, x equals water saturation. Y, I'm not going to give it a y yet. I'm going to give it color equals agricultural treatment. And that's all. Okay. Then I'm going to say geom point. And in here, I'm going to set the y aesthetic. Y equals plant mass. Okay. And then I'm going to give it another geom point. Well, first the line. Geom smooth, I mean. Geom smooth. Aesthetics, I do have to tell it y again, since I didn't set that aesthetic up here in the main part. Okay, geom smooth aesthetic, and I'm going to say method equals lm plus geom point. So I'm going to do another geom point where my aesthetic y isn't plant mass, it's pred, our predicted stuff. And then I'm going to set the color to black. And size equals 2. Oh, and I forgot to add a facet wrap based on, or as a function of plant species.
Question.
Yes.
Why, when we do the aesthetic for both the geom points, do we do y equals and then specify?
Because up here in my main, for the main plot aesthetic, I didn't give it a y because I wanted to be able to change the y aesthetic in this geom point and this one. So
Okay.
in other words,
They're
for the
individually.
first geom point, it's going to do the actual data, my plant mass. The second one, I'm having it use the predicted values by the model.
All right, and the smooth line is going to be for your actual data as well.
Actual data, yeah. And so here's what we see. All right, what are we looking at? It's our old plot again, but with something new.
So your predictions are going across your lines, which is good, right?
They have to.
Oh yeah.
They have to be on the line because that's what our that line is our model, just represented graphically. And so what these black dots are showing are the predicted values based on that model. So they're always going to be right on the line. Okay.
So how does that add information then if it's already going to be on the line?
Right. How does that add information? It's a good question. What if we go outside of the line? You know, or what if we wanted to predict a value of, instead of 50, 51? Right. So it allows us to visualize our predictions. And we can predict outside. This is not always a great idea, as you'll see. We can predict outside of our data, so we can extrapolate further. In other words, if we only did our experiment with 10 through 50 of our water saturation, and we calculated a best fit line, we could predict what things would look like at 75% water saturation. Whether or not that would reflect reality is a very different story, but it'll allow us to do that. Okay, let me try something else here. Gather predictions. So let's look at, show a few models. So gather predictions. Our data is DF. Our models are mod 1, mod 2, and mod 3. So here, it's used all three of those models that we made and has made predictions based on them. So let's take a look at this. DF3, I'll save that. And then we'll basically make the same plot. DF3, red, facet wrap species, and I'll do model. Is it called model? Yep. This will be a big, stupid plot here, but okay. So this first column is model 1 and its predictions. The blue and red dots and everything is the real data. The black dots is what that model predicted. So looking at this, what do you see?
That it looks like, actually, freak if I know. I was going to say that our third model is the best because everything's along the lines. Our first model was the worst because the black dots are the most separated from our lines.
What I'm showing you is the difference between the three models that we made. One of them only took water saturation into account. So it's only able to make one set of predictions based on water saturation. Does that make sense? That was mod 1. And so in reality, we've got these different agricultural treatments, right, and different plants. It doesn't care. It's giving the exact same values for each one of those plants. If you look at this, it'll be the same points or the same like plant mass value that it's predicting. Doesn't matter what plant it is, doesn't matter what agricultural treatment. All it takes into account is water saturation. And you can see it doesn't fit our real data very well. Model 2 took into account agricultural treatment, plant species, and water saturation, but it did not allow the slopes to vary. So you'll see that the distance between any two of these points here is going to be identical all the way up. They've got the same slope. Model 3, since we changed the pluses to times, allowed the slopes to vary. And so we've got larger difference here than we do there. All right, so this is just showing our 3 models against the backdrop of the real data. So let me maybe alpha equal 0.5, make that a little deeper into the background. Kind of obscure the junk in the background. Yeah, I don't know if that helped or not. Okay. What was I trying to say? I don't even remember now. Oh yeah. So you can see how the second model does a better job than the first one because it allows the prediction to vary based on agricultural treatment, but it's still not capturing the real spread of our data because it doesn't capture that interactive changing of the slope. Okay. So I'm going to go with that third model. Summary mod 3. Okay, so there's our statistical table that we report in our presentation. What were the terms that were significant? Well, our intercept, okay, that's fine. Water saturation, that's got a really low p-value. So we can say in our data, water saturation is a significant predictor of plant growth. Agricultural treatment was also significant. So was being plant species B as opposed to A, and C as opposed to A. And then this, what's that line mean?
Agricultural treatments effect on plant species B?
Agricultural treatments, the effect of agricultural treatment depended on plant species, with plant species B having a significant interaction. What it's, in mathematical sense, what it's saying is that for plant species B, the slope of the line depended on agricultural treatment. Okay, so this table here, with all its confusing gobbledygook, is actually just mathematically describing the picture that we have. Okay, and the estimates are the effect of that particular predictor on the slope of our line. The estimates that aren't significant, we can just disregard, right? Those aren't actually important in our data set. The other ones, we can then go write our little paper or report on this and say that, hey, the agricultural treatment is important and it has this much effect overall on plant growth. Okay, on average for all 3 of these species, plants had 0.57 grams greater mass if they had the agricultural treatment. Okay, water saturation also was important and went up at this rate with each increase of 1%. Okay, you can also say that, however, for plant species B, the effect of water saturation was lower than for plant species A and C, or than A. And for plant species B, the same thing. Or actually, it was higher. Positive slope there. Further, you can say that agricultural treatment for plant species B had a different slope or different effect over the course of water saturation than the others. Okay. All this right here is essentially the entire data analysis kind of pipeline. It's obviously going to be a lot worse if you use real data that is messy and stuff. You're going to have to clean it up first. But once you visualized, it really comes down to just trying some models, finding which one is the best explanation, and then looking at what that model is actually saying.
Question.
Great.
So once we clean up real data, is it that simple for the models, or
Yeah.
is real data okay? Because I was like, I'm wondering if real data, I'm going to have to try 20 different models, but you can just take a look and kind of figure it out within like
You
5.
take a look, and okay, so it becomes more complicated depending on the type of data that you've got, right? This is the generic, we're measuring a continuous variable as our output, right? And it's more or less normally distributed. So we may have to transform our data first, right? If it's not normally distributed, we may have to do a log transformation on it first, but then it's fine. What if your output variable is binary though, like something occurring or not, right? Then you can't use a generalized linear model. You have to use what's called a logistic regression. Okay, so we'll get into that. It all depends on the sort of data, but it's all still this easy. All of the models in R follow the same format. We have a model family that we fit. We give it our data, and we give it an equation, and it's that simple. And then we can say summary and look at stuff. Okay. There are hundreds of different stats packages available in R for fitting all kinds of different models. Right? So maybe you don't want a linear model. Okay, maybe you want a model that doesn't have to follow a straight line. Well, there's built-in stuff for that also. But in general, yeah, it really is this easy. And we're going to definitely start out just doing GLM type stuff, maybe ANOVAs. Once you get the feel for that, taking on a new package of models is a matter of minutes to kind of learn how to use it because it follows the same format. And there is our statistical test results right here. So I mean, that's our output. Yeah. It's the easiest part of data analysis is actually doing the stats tests. The hard part is getting the data loaded, getting it cleaned, visualizing it, and coming up with what a good model might be. Okay. Something important is that this model is not correct. There is no such thing as a true model. A model is a mathematical simplification of reality, and so it will never be 100% right. But that doesn't mean it can't be useful. We can still get good data. Right? The idea is that we're going to try to find the best model we can and the simplest model that we can. And so that's why we do a few, kind of compare them, maybe plot the model alongside our real data like this to kind of like get a feel for which one is best explaining things. Okay. But that's our output. And in essence, that's a completed data analysis project right there. This one was pretty straightforward because it was nice and clean coming in. A dirty one, we'd have to take a while getting it cleaned first, but then it would be the same stuff. Plot it a few different ways, get a feel for the data, think about what a good model might entail. So which explanatory variables do we want to include? Some might not be useful. And then model it, get your results. A lot of times you'll have explanatory variables that aren't useful at all. For instance, if you're looking at like somebody's grade in a class, you could go out and collect their shoe size, right? And you could throw that into your model and it would probably have no effect whatsoever, right? There'd be more important things for explaining somebody's grade in a class, like amount of time they studied or previous classroom experience, stuff like that. So your real data sets out there in the wild may have a bunch of stuff that just isn't important. And so you can start out with a really complex model that takes it all into account, see which things are or are not important explainers, and then just kind of whittle down your model to only the important stuff. And we'll get practice at that. I really wanted you to kind of see this magical process and kind of see behind the curtain. It's not too difficult. There's nothing magical going on, and the reason so many people use R for data analysis is because all this stuff's just built in. You can just say GLM, right, and it's done. If you want to do an analysis of variance, mod 4, it's AOV, right? Same sort of deal. Data equals DF. Plant mass as a function of water saturation times agricultural treatment. Okay. Boom. There's mod 4. Your table looks a bit different because we use an F test since it's an analysis of variance, but it's the same sort of deal. Here, though, in an analysis of variance, we're not actually doing a linear model necessarily. We are doing a regression behind the scenes, a one-way regression, but it's not reporting the estimates for you. It's just saying if water saturation was important. It doesn't tell you the direction. If agricultural treatment was important, and if the interaction was important. In this case, it's saying no, okay, because we didn't include plant species. So that's an analysis of variance, just AOV. We could do a Tukey test on mod 4. No factors. Oh yeah, right. So we have to change those into factors. Oh, not that one. That's not a factor. Factor. So here it's saying the difference between true and false. True minus false, the difference is 0.776. Okay, so that's saying the true, the agricultural treatment that they did receive agricultural treatment is expected to be 0.776 higher. That's the same number we got with our linear model because that's actually what's being run in the background with analysis of variance. We can plot that. And here it's just saying there's your average increase from having the agricultural treatment. And here's your 95% confidence interval. So we would expect 95% of the true values to be, how to say this? 95% of the time, our model would find the true value with this error rate here. Okay. So all the modeling in R is pretty much this straightforward. We'll see some more complicated examples starting next week when we really start digging into this. But I hope this kind of made sense for you. Maybe. Ernie?
So is this what's expected of us, our final project?
Mm-hmm. You know, but with the cleaning also, your data is probably not going to be nice and clean. What I expect out of you is also to turn this into a report, and we'll see how to do that. Yeah, maybe in a few weeks.
Okay.
Yeah. Because R can actually write your report for you as well. If you want to see Desktop, Git repositories. So here's my syllabus for this class. I wrote it in R, and it can convert it into an HTML like web page, essentially. It's as simple as like 2 little asterisks mean bold. 2 stars mean header size 2. This is how you make a table, right? So we're going to incorporate this kind of like markdown text along with the code to generate a full report. But the full report will be stuff like, here's a test of some of my models. Here's the statistical output from the table. And then here's how I'm interpreting that. And so it's going to be a full report with like background, here's what the data is about, here's my cleaning script, here's my results, and here's how I'm interpreting them. Yeah.
Okay. Cool.
All right. Any other thoughts? All right. Was that meeting with somebody? Is that you, Ernie?
Yep.
Okay. So I'll just stay on here. Everyone else is free to go.
And
Have a nice break.
is the exam due Monday before the test? Before Monday before class, right?
I thought it was, yeah, before class. Yep. So what I'll do, I probably won't do a Git pull until like Monday morning. So even though it says it's due Sunday night, I'm not going to be up at midnight pulling your Git repository, hopefully. So I'll wait until Monday morning to do a Git pull.
Okay. Cool. All right. I just wanted to like